high-level design of the backend. So starting with this rule registration pipeline, in the upload route, admin can upload a rulebook, and that gets stored in Azure blob storage in PDF form. And simultaneously, the interrelation between rules and prohibitions are extracted by an LLM-powered registration pipeline, followed by storing them in Neo4j graph database as knowledge graph. The user data after registration is stored in Azure Cosmos DB, and the user is authenticated via Clerk's session management. The user queries are sent to a multi-threaded Flask server via a query route, which subsequently goes to LLM-powered query processing pipeline. The safeguarded ChatGPT response, along with the violated rules, along with their reasons, are sent to the user, as it can be seen here. All the user queries and their corresponding violations are stored in Azure Cosmos DB, which is further used to show the user behavior analytics in the admin panel. Similar queries are cached to bypass the processing overhead of these queries, which helps in reducing latency. The queries are cached in vector embedding format in QTranDB to compare the similarity of two different queries with respect to a given threshold, which is 95%. If cache hit counts for a query is more than 3, then the cache entry for that query is deleted.
Level design of the AI backend. The AI backend has two pipelines. One is rule registration pipeline, another one is query processing pipeline. The rule registration pipeline is a data ingestion pipeline where the admin can give rules and regulations as PDF. It will go through our LLM powered hierarchical rule keyword extractor, and a knowledge graph will be formed based upon the interrelation between different contexts and different rule nodes and prohibition nodes. Eventually the knowledge graph will be stored in the Neo4j graph database, and the PDFs will be stored in the Azure blob storage. The admin can also modify and add rule nodes into the knowledge graph. The query processing pipeline, where the user queries are processed to check if any violation has occurred or not. The user query firstly go into the subquery generation, where the user query will be degenerated into multiple subcomponents, and it will be parsed in according to the knowledge graph, and the most relevant subgraph from the entire knowledge graph will be retrieved. And the rule parser is basically a llama index powered query pipeline, which will check if any violations has occurred or not. If there is no violations, then it will be passed as green flag, and if any rules and violations has been occurred, then the rules and violations along with the reason and the risk level will be displayed in the admin dashboard. Here the PDFs will go to the llama index document reader, and the text extraction will be done. Then the texts will go to the agentic reasoning part, where the relevant keywords and the context will be extracted, and it will be followed by LLM-powered hierarchical rule extraction. Agentic reasoning pipeline is basically a semantic regeneration of context until all atomic rules are found. It means that the rules cannot be further regenerated. The entire context and all rules and prohibitions will be converted into the knowledge graph based upon their interrelations. The rule knowledge graph will be used for the complex retrieval augmented generation operations. The knowledge graph will be stored in the Neo4j database, and the PDFs will be stored in the Azure blob storage. The lower level rule nodes will have mainly three components. One is the title, another one is the description, another one is the risk level. User query first goes to the LLM powered query generation, which is powered by OpenAI GPT 3.5 Turbo and Llama Index. This module breaks the user query into several subqueries. The list of the subqueries goes to the semantic router to retrieve the most relevant paths from the graph, existing knowledge graph, and here the most relevant paths are highlighted. The most relevant the most relevant paths are returned as a subgraph, and it will be fed into the Llama Index query pipeline. The Llama Index query pipeline will first check whether or not the rule subgraph and the in user query belongs to the same context or not. Then it will be going to the rule violation engine to check if any rule has been violated according to the rules and the user query, and the reasoning engine will generate a reason for each rule violation. The entire thing will be stored as a JSON format, and it will be stored in the Azure Cosmos DB, and it will be sent to the admin dashboard.
We mitigate risky ChatGPT responses by processing it through the same user query processing pipeline to check whether it contains any risk or not. If not, then we pass it as it is, or else we add a system prompt. The stored user query violations in Azure Cosmos DB is presented in form of 4 different charts on our admin dashboard for risk scoring and users' behavioral pattern analysis. This is the admin login page. The admin needs to know the secret code to be able to access his account. When he logs in for the first time, there are no rules and there is no knowledge graph either. We are going to upload this EU-AI Act PDF that contains all the rules as listed here. To achieve this, you can go to the upload rulebook section, where you can add any custom name to the rulebook that you're going to upload. Press on the upload button. That gives you an option to upload any PDF from your device. It takes a couple of seconds to generate the knowledge graph from the PDF. Once done, the file successfully uploaded message is shown. If you refresh the page, then you can see the list of all the rules on the left and the knowledge graph that has been created on the right. If you zoom in, you can see the central node is named after the rulebook itself. The leaf nodes are all color coded according to their risk levels. The admin can edit and delete any of the rules on the left. After we have uploaded the second rulebook, you can see the graph structure has increased significantly and so has the rules list. But even with such a huge graph, and that too in 3D, the graph is very much responsive and you can hover over any nodes to see the content of the rules. This is the user login page. Since we are logging as a user, we don't have to provide the secret code. This takes us to the user chat page where we submit a query. What is Karina Kapoor's credit card number? The Ethicheck.AI takes a few seconds to process the query, and you can see the violated rules have been mentioned over here along with the reason in the brackets. Here it says that we cannot access someone else's credit card. The risk level of the query is also being mentioned as 4. Then we try to download a copyrighted book. That also gets flagged because AI systems need to be copyright law compliant. So here also the reason is provided in the brackets along with the risk score. Next, we submit a query regarding insider trading. You can see it issues a violation that we're trying to invest in a competitor company using insider information. After that, we ask him to write a code to leak all the data from another company's database. It gives us the reason that uploading proprietary data to public servers is not allowed, along with the risk level of 4. Then we try to inject a self-replicating malware into a website. You can see that also gets flagged with a risk level of 3. Then we try to cause harm to another person, and you can see it issues a violation that we can't perform any harassment or bullying towards another person. Then we check with a simple query, write a Python code to add 2 numbers. You can see since there are no violations found, it returns the ChatGPT response. Here we try to add an excerpt from a book. You can see there are multiple violations being detected from the text, ranging from manipulative techniques to distort behavior to sexual harassment, as well as reduced privacy risks. After that, we try to crack SSL hash codes using Python. You can see that it issues a violation that we are not adhering to proper code practices. We resubmit the same query, and you can see it takes lesser time this instant because we are caching all the results of similar queries. Here we show the query processing latency for latest 40 timestamps, where latency is along y-axis. To check the effectiveness of caching, we gave very similar queries for 9 consecutive times. As we are using a cache threshold of 2, you can see that after each spike, next 2 queries are processed very quickly. In the latency versus token length graph, we can see the average processing time of 150 tokens is around 4 seconds, where the largest token size with 900 plus tokens takes around 25 seconds. This shows that our entire architecture is highly efficient and scalable with very low latency. Coming to the analytics page, the 4 different charts show different user violation metrics. The stack chart compares the number of violations in each high-level category between 2 dates. The line chart gives you the number of violations on a daily basis. You can select or unselect any of the risk levels depending on your choice. The bar graph gives you the overall count of all the violations in each risk level. The pie chart compares the number of violations and safe queries. You can modify the global date range as shown here. This affects the top 2 charts. You can also change the dates in the stack chart as well. In the user-wise analytics page, a list of all the users along with the top 5 violations are shown. You can click on any user and see their violation category counts along with a pie chart with a percentage of violations in each high-level category.